University of Tennessee, which relates to molten salt reactors, dynamic system modeling. I will talk about some models which we have developed, which are all openly available on GitHub. And I will talk about some applications of this modeling as it relates to safeguards and some of the fresh work we have just done, as in 1 a.m. this morning, which relates to decay heat modeling. I would like to recognize Flight Energy, UT Bethel, and DOE and Terrestrial Energy in alphabetical order. Maybe like 6 years ago, I was making the case that one of the problems we have in this universe of molten salt reactors is the lack of trained students, which we need to design, operate, license these systems. So this is why I took this job in academia. I was working on reactor core modeling, how it pertains to safeguards, dynamic modeling, which will be most of this work, and xenon behavior, which is still sort of question I think we have to pursue with much bigger vigor than we have thus far. So I'd like to report that in the last 6 years, minimum 200 students who graduated from UT have some knowledge of molten salt reactors, meaning they have heard about it. I told them at least a couple sentences about that. At least 50 have actual research experience at undergraduate research level, either directly with me or through the senior design projects. Let's say 15 graduate students had participated in some molten salt reactor research. Most of the work which I'm presenting is actually done by graduate students Vikram Singh, Alex Wheeler, and Visura Pathirana. And here is a thesis of Vikram, who recently graduated and is now working for Flight Energy. Here are some publications we done in the last 2 years related to the work I'm presenting. Dynamic system modeling is a simple way to model the system behavior that captures the underlying physics. It's adaptable to different systems, and once you have dynamic models, you can ascertain transient behaviors of these reactors. You can model what happens during the transients, maybe accident scenarios, without breaking the bank on computational requirements. It's very useful for developing instrumentation and control, because then you can plug your instrumentation and control models into your dynamic system model and see what's going on. It's also useful to find out safety limits of operation and sensitivities of parameters. So these MSR models have hundreds of parameters in it. They correspond to some physical variables which we don't know in detail, and we can figure out which one of them we actually need to know to be within some safety envelope. Part of our effort is to develop the validated open source tools that everybody can use. And all this work is built up on work done by Sid Ball and Tim Kerlin back in the 1960s and 50s. I'm excited that both of them are in the audience, so that's wonderful. So here you can see the paper from 1965, Oak Ridge TM 1070, and a plot from that. So I hope the questions won't be too rough. So what models have we developed? And these are the models I will briefly talk about. We have a molten salt reactor experiment, which you're familiar with. So this is basically a modern version of the model back from 60s and 70s by Sid Ball and Tim Kerlin. We have a modified point kinetics equations for the core modeling. We have a primary heat exchanger in the radiator model, and this has been, to the extent possible, validated with the MSRE data. Then we have a model, the two-fluid molten salt breeder reactor, and a single-fluid molten salt demonstration reactor. And here's the sketches of the power plants. So let's talk about the molten salt reactor experiment modeling. In the simplest model has a one node for graphite in the core and two for the fluid. The fluid enters the core, warms up, then goes through the primary heat exchanger and then back in the cycle through some delays. And then the coolant salt enters the heat exchanger, gets some heat, and enters the heat exchanger, gets the heat, and through the delays dumps it in the radiator. So these are the two circuits you see in Molten Salt Reactor Experiment. This would be the one region model, but we can also partition the core into 9 regions like the Oak Ridge has done in their paper. And then the dynamic feedbacks are calculated separately in each of these nodes. We have developed this model in MATLAB Simulink. You can download it from GitHub if you are interested. So if we look at some models, results from the model, you see what happens if we insert an PCM of reactivity into the core when the core is operating at 1, 5, and 8 megawatts of power, whether it runs on U235 fuel or on U233 fuel. You see that the U233 fuel having a smaller delayed neutron fraction acts quicker, and that the 9-region model allows you to resolve a faster time scale in its behavior. A lot of our work relates to frequency characteristics. As a function of frequency of some reactivity perturbation, you have to say you have a plus minus 1 PCM oscillator connected to your reactor system, you can see how the system responds. And there are 2 parameters of interest. One is the amplitude, so how does the system amplify the signal at a particular frequency, and the other one is phase shift. What is the phase shift between the forcing amplitude and the phase shift of the response? On the top plots is the magnitude, and what you see on the bottom plots are the phase shifts for the U235 and U233 fuels. Now you see that there is a peculiar feature here. It's a dip at about a quarter radians per second, and that corresponds to the primary loop circulation time. It's a sort of an inherent frequency of the system. If you imagine that the small mass of salt is entering the core at the bottom, then the fission occurs, and the mass in this mass which enters, it flows through the primary circuit when its delayed neutrons are decaying before entering the core with a certain time. So basically you can understand it as a inherent frequency characteristics of the system. And this data, the black dots, are the MSRE measurements. We digitized them from the peer-reviewed papers. They're available for other researchers on GitHub. But it might be non-intuitive to interpret, whereas time response to reactivity insertion is more straightforward to interpret. Unfortunately, we have found some problems in the MSRE data. Note that this is not from a peer-reviewed paper, just from an internal report, where we have seen that the response at 5 megawatts to plus 19.6 PCM of reactivity looks reasonable in the models, but the reactivity, after the reactivity insertion of 24.8 PCM at 8 megawatts, what we are seeing is much higher response than what was reported. Now, if you say that this was not 24.8, but 14.8, postulating there is a typo in the report, we can actually match the reported data quite well. So I want to just point this out to say that the MSRE data are not perfect. This was not meant to be a benchmarking machine. It was a machine to show that these things can work and do some development on. And the benchmarking prototype, so to speak, of a validational prototype was supposed to be a follow-up work, which has never happened. So we may never know. Of course, the MSRE is unusable right now, so that's a mystery. I spoke about the modeling of operational anomalies and accident transients. What happens when your pump trips? We can model that in our tools. We can postulate some times from 2, 6, and 10 seconds of the coast down time of the primary pump. And here we see what happens to the fractional power. And here you see what happens to the average core temperature during that transient. Another reactor we modeled was this two-fluid molten salt breeder reactor. It has the two fluids. Here you see the core fluid with fissile material, which enters from the bottom, goes through the channels, comes out, goes through the pump to the heat exchanger, and back again. And then you have the same thing happens with the blanket fluid, which enters here, goes into the blanket region to its own pump and its own heat exchanger. And the core is made of these hexagonal lattices, where the blanket contains thorium, is in the interstitial region, also surrounds the core. Then we have a graphite channels with two sub-channels, one for the fuel going down, and here in the semicircle, fuel going up. The gray is the graphite of the channel. So the model here is slightly more complex, as you can tell. The fuel enters here in the middle and goes up, is contact with one part of the graphite, and then goes down in the channel, and then goes out into the heat exchanger and back in the loop. The fertile salt is here. It goes through here through its own fertile heat exchanger. And the coolant salt extracts the heat first from the fuel and then from the blanket, and then goes to the, part of it goes to the reheater, part of it goes to the boiler, and then it gets mixed back into one stream and goes back into the primary heat exchanger of the fuel and the primary heat exchanger of the blanket with appropriate time delays. We studied behavior of this system at different powers. Here you see 56 megawatt thermal, 256 megawatt thermal, and 556 megawatt thermal, which is a nominal power of the system. So actually first modular reactor, as far as I can tell, where you have four modules, each 556 megawatt thermal, but they are connected to 1 gigawatt electric turbine. So we are modeling one of these systems. And you see that the higher the power, the faster the feedbacks work. This is the response to reactivity insertion. And here you see at full power what happens when you add reactivity into the system. The power spikes, temperature feedback pulls the power down. And here you see how the feedback acts. So if you insert some kind of reactivity into the system here, then the feedbacks will counteract that reactivity as the fuel and graphite heat up. Again, we can study frequency characteristics of the system. Here we see a two characteristic dip, one at 0.3 radian per second, one at 0.1 radian per second. And the dip at 0.1 radian per second corresponds to the coolant loop time, and the dip at 0.3 radians per second corresponds to the power-weighted average of the fuel salt and the fertile salt loop times. We also looked at load following with the system, where the core is entirely demand-driven with no control element action. In this case, we start at nominal power and we go back to 50. We go down to 50% at 1% per minute, and then we go up at, back to full power at 1% per minute. This is the zoom out of this departure region. Here you see the demand power, and then you see the core power in blue, and a temperature as we could measure it with some temperature sensor. Something I have realized about molten salt systems is that they are low pressure systems with a constant flow rate. So what happens when you are changing power with these systems is you are just changing delta T on the core and the heat exchangers, with while the low pressure fluid is smoothly flowing in each loop without any pressure waves or phase transitions. So we see that we can load follow very quickly. Now the question is how quickly. So we took this model and we tried to break it by doing rapid load follows. Starting with some slow ones. So this is a 1% down to 50%, 1% up. This is the plot you have seen. And what you see here is the temperature of the hot leg and the cold leg of the primary system, right? So you see that as you lower the power, you lower the delta T across these heat exchangers. Now, instead of 1%, we go by 5%. Well, still no problem. Here is our temperature limit, the liquidus temperature of the molten salt. What if we go at 25% per minute to half power, and then 25% per minute to 1.5 nominal power? And so you see that the only time where we are in anywhere near the zone which we would like to avoid is if we are ramping up the power very rapidly, and just before we equilibrate, we can undershoot. This is transient. We can sort of get close to the temperature of the cooling of the salt. Now, this is no decay heat. This is no heaters, so it's unlikely to freeze in reality. But I thought that this was an interesting find where your safety limits are in a very rapid load follow. Now, this is likely much faster than any balance of plant would allow you to go anyway, but it's quite remarkable to see. And again, this is all demand-driven with no control action. If you have control element action, you could most likely smooth out these temperature transients. All prior models were models of the core, heat exchangers, different salt loops, and we didn't model the balance of the plant. So we modeled the reheater and the boiler, but we didn't model anything beyond that. In this model, we have the model of the entire plant, including the Rankine cycle balance of plant. So you see the core here with its primary loop, secondary loop using a similar salt as in the primary loop, just without the fuel. Then we have a third loop, which is using solar salt, this high-tech salt, sodium potassium nitrate, and that transfers heat into steam generator. We made sure that our salt actually doesn't freeze in the steam generator, and that creates steam and runs your plant. I have to go quickly. So here is a nodal model of the primary loop, secondary loop, tertiary loop. Then we have the ones through steam generator modeled as a variable boiling length, and this is the steam cycle. What matters to the dynamic behavior is the steam generator. The rest of the balance of the plant doesn't affect the system behavior. So here you see the frequency characteristics again for the gain and phase. And this is the red line is the full model with the balance of plant, and the dashed line the blue dashed line is just with the steam generator, and the yellow one is without steam generator, just with the constant heat removal from the salt loop. So the balance of plant has over 100 state variables. The model has over 100 state variables. It's a very complex model, so we would like to not use it unless we have to. So that's useful. Here are some load following transients, again, demand-driven, and the model seems to work. I have to speed up a little bit. Briefly about sensitivity analysis. These models have hundreds of parameters, which corresponds to some physical variable or constant, which relates to the reactor system. Many of them actually evolve with fuel cycle as you deplete the fuel. Measuring these is expensive and time-consuming. So if we can determine what is the sensitivity of each of these parameters towards the safety limits of the system, we can set up research priorities and only focus on the ones which actually matter for our safety case. So that's why using these models for safety analysis is useful. Now here you see that we have perturbed select parameters by plus minus 15%, and how the system responds to plus 20 ppm reactivity under those perturbations. So I won't go into it in detail, but you see that some of them have no effects, whereas others have large effect. So if you apply this to some transient, which may have safety implications, we can nail down what we are interested in. We can also study this in frequency domain. The advantage is that we don't want to insert large reactivity into our system while operating, whereas because they induce temperature changes, we can induce a small oscillatory periodic reactivity insertions and see how different parameters change. Now this we applied to a different topic called safeguards. So any reactor which is supposed to be built, licensed on international markets has to have safeguards. IEA requires you to detect in a timely manner 8 kilograms of plutonium diversion, and we have no agreed upon methodology for safeguarding MSRs. Traditional item counting is not applicable to liquid fuel. So we have to come up with new ideas how to safeguard nuclear materials in molten salt reactors. Now, liquid fuel actually has a lot of advantages and opportunities how we can do safeguards differently and smarter. For instance, if we sample the fuel, we can keep time capsules representing the entire core isotopics and go back if we need to recover, say, from loss of knowledge incident. But what I will talk about is, can we use these frequency analysis to detect one significant quantity of plutonium? If we just have a core after the removal of plutonium and we do the reactivity insertion, in small core, the significant quantity would take all the plutonium out. In a large core, it would only take, say, 15%. We see that the difference in the peak response is small and hard to measure. Now, if we do the frequency analysis for the base case and for those two when we remove the amount of plutonium, and we look at the difference in the response, we see very specific structures in both amplitude and frequency responses, which are fingerprint of plutonium diversion. And this is something you can do online without disrupting the operation. Much better way to detect plutonium diversion. We also implemented a decay heat in a novel way. We'll publish a paper soon, and this is the stuff which was 1 a.m. this morning. And I would like to, as a last slide, show you what happens in molten salt reactor if we lose the heat sink. As we lose the heat sink, we drop 1,000 PCM of reactivity, and we open a decay heat removal system. So what you see here is that the power, which is composed of fission power in blue and decay power in Cherenkov blue, goes down as soon as we drop the rods, but the core is still generating decay heat. Temperature in the core starts to go up, and now it's getting removed with by the decay heat system. As the temperature goes down, the feedbacks kick in, right? And at some point, your core will be critical again, just at very low power and lower temperature. It's because the core will stabilize itself and take care of itself so it doesn't freeze. We just maintain its lower temperature after you drop the rods in. So I thought this was a fun result from our dynamic modeling to show. So here are my conclusion slides, and thank you.
Are there any questions for Ondrej?
Does your load following give any burn-up efficiency gains?
If you lower the power, right, you use less fuel, obviously. Yeah. So you can do it. Now, of course, anytime you have a system which has a high investment cost and low marginal cost, you want to run it all the time, right? This is simple economics. But you can load follow very rapidly with these systems. And now we are getting into a situation where load following has its own income streams, right? Like a grid services. So that might change this economics case and say, okay, if you can load follow, you can actually make more money even in this situation because load following becomes so much profitable now. So.
Very good. That's all the time we have for that, but I just thank you so much.
Thank you. Thank you for having me.
I wanted to say that Ondrej was at our first conference 10 years ago, and he was a student then, and he's a postdoc, well, still a student, and and now he's a big man, you know, working at UTK. So you're a great success story. I mean, I'm so proud of all the work you're doing.
Thank you.
And I wanted to show, you know, out of the gate, you know, a younger generation is picking up, you know, where, you know, all the tools were left on the ground for about 30 years. You know, you're rediscovering them and inventing and creating new ones, and it's very inspiring work. So thank you for all you're doing. Thanks again.
Thanks for having me.
Yeah, absolutely. Don't steal my mic.